I've got a sticky note over there. Just hit presentation.
Yeah, don't, especially if it's been scheduled through Zoom. You shouldn't have to do
'cause
anything else,
well,
just share.
But you have to know to hit presentation.
Or-
You don't know to hit presentation.
Yes,
You just-
you're right.
All right. All right, good morning, everyone. Welcome back. All right. So today, it looks like we're going to go through tributary area, wind load versus dead load, racking versus translating, deflection, thermal expansion, splices, and how these items are indicated on drawings.
Yeah.
So we'll go through that. Thought I'd just call up. I used to have a little presentation and I can't find it on the servers anywhere, so it's been deleted. So we'll just sort of go through a job and just sort of indicate what we're talking about when we talk about tributary area. So again, this is all regarding load. Most of this is loading to the building and then movement on the building as well. And so you guys are probably familiar with tributary, maybe you're not. I don't know. But as it relates to our anchors, we look at the tributary area and then deflection as well. So on this vertical mullion right here, as I'm considering its deflection, its tributary area is going to be half of the width of the bay on either side. So that little box right there that I got. Oops, come on, get out of there. I don't want that. User error.
I think they were having issues with the keyboard this morning.
Okay, so as I'm considering when trying to determine the deflection of this mullion and wind load, the tributary area that's contributing to that deflection is going to be the wind load on this half of this piece of glass and this half of this piece of glass. For the full height of the mullion.
First, can you define what deflection is, and then?
So deflection is the bending of things. So whether it's from dead load or wind load, things, floor slabs deflect when you put a bunch of people on it. So the building engineer, when they're looking at their structure of their building, they've got to worry about live load deflection. And so again, deflection is when you have loads applied to. And so it can be dead load deflection, it can be wind load deflection, it can be seismic deflection.
So it's in different directions.
Depending on,
right?
it's
So
in the direction of the load.
Would be
It's
deflecting this way,
because the load is vertical.
pressing down,
Yeah.
right? And then you're saying what you're looking at here for a vertical member is deflection in and out.
That's correct.
So that vertical member bowing,
Yeah.
is the deflection.
So if I can find a mouse, where's my little keyboard?
Need a PDF.
So yeah, we're gonna have a little technical difficulties, it looks like today, so I apologize in advance as we're finding it out. So yeah, as we look at a section, and as it's talking, we're considering deflection on this, we're looking at, how this mullion is gonna bend in under positive wind load. So that's wind load that's blowing this direction. And then in negative wind load, or that little vortex that we talked about when we talked about corner zones. And so it's not that it's a negative wind load, but it's really a negative pressure zone that's pulling the glass out. So the shapes and the red lines, that's going to be the mullion deflection that we're going to see. The specifications give us the criteria for that. Our normal deflection criteria is L over 175, where L is the length. So if you ever see an L over 175, the little L is the length. And then they'll also stipulate a lot of times 3/4 of an inch max. And so the 3/4 of an inch max isn't a metal fatigue issue or anything, it's a glass issue. And so in this light, it would be similar to this light of glass, but let's say that one light of glass from the sill down here at the bottom, from the sill to the head up here, the glass manufacturers have their own little thing that they sort of add in. In any one light of glass, they don't want that edge of the glass to deflect more than 3/4 of an inch. So that's where the L over 175 or 3/4 max comes from. And so a lot of, if this horizontal in the intermediate, Apologize, Amber. Oh, come on.
You just have to click to get it.
Is that, oh, you're right, there it is.
Yeah.
So if this horizontal was down here in the middle, and the mullion deflected 3/4 of an inch, none of the lights of glass are actually deflecting 3/4. The head has moved over 3/4, and now the deflection is within that. So typically when you have multiple lights of glass in a span, the 3/4 of an inch, while the specs still ask for it, and so a lot of times we still try to hold to it, we're never going to have that issue with the glass. It's really when I've got an opening that's where it's a really tall light of glass. And so we see that a lot in our curtain walls though now too, is where, you know, the architects are wanting larger and larger areas of vision glass. And so that comes into play there, just ensuring that we're not over deflecting on the glass. And in reality, the glass manufacturers can sometimes go over that 3/4 of an inch if you ask them, and you know, it gets sort of special dispensation or whatever. That's just sort of their industry's general rule of thumb from the glass manufacturers. The specific glass manufacturers, if you ask, we can sometimes go over that. And so that L over 175 3/4 max on projects, especially curtain walls and things like that, where we'll see a sort of differentiation on that for applying that load for spans 13 feet 6 or less. And then once it goes over 13 foot 6, and so when I say span from anchor to anchor, if that span goes over 13.6, then we can use a different deflection criteria of L over 240 plus 1/4. And essentially, it works out to be about the same if we do our math. So if I'm 175 over 175 is 1 inch. If I do 175 over 240 and then add 1/4 of an inch, I'm going to get 0.98 or 0.99. So it's really, it ends up just coming back to L over 175. It's sort of doing away with the 3/4 max. It's not exactly L over 175, but it's fairly close. And sometimes they just tell you it's L over 175, and then that can just keep going forever if they want. So really, it's driven by the specs, but those are the two we normally see in vertical mullion deflection. That's just fun. So yeah, so in this vertical mullion here, you see it's got a 14-foot floor to floor. So as we're analyzing this mullion here for its deflection, you know, I can come over here and I'm allowed to actually go over that 3/4 of an inch number a little bit.
Just because it's greater than 13 foot 6.
Exactly. And then because I've got the intermediate horizontals, I'm not really worried about this light of glass deflecting more than 3/4 of an inch. So I still have to maintain that. Even if I can allow for the metal to go over the L over 175, the glass, each individual light of glass can still be 3/4.
So you're really looking at, you're looking at two things. So you're looking at the vertical mullion itself, anchor to anchor.
Yep.
So that's the aluminum.
Correct.
Then you're also looking at the glass.
Correct.
If it's a big span.
Yeah, right.
So then when you say 3/4 max, is it 3/4 from the face? Like where do you measure it from for the glass? Is it from the face in the middle, the worst point? Or like you said, just the tips?
Right, so yeah, so then, I apologize for that. So then let's say on this one, well, let's come back. We'll come back over here and imagine that there was a horizontal right in here, that I had my little horizontal right here. So when that horizontal moves in 3/4 of an inch, with, you know, my glass is actually at an angle now. So it's doing this on a piece of glass. Oh, that's crazy. There you are. And so now the deflection, let's get rid of this one. Now my glass deflection for this light of glass starts from there. So it's already in 3/4 of an inch. And now the glass deflection actually starts from there as it's coming down. So then as I'm measuring the glass deflection, I think I'm measuring it right here.
So you're measuring at the worst case, imagining that mullion is deflected also.
Yes.
Okay.
The glass, well, because if the glass deflects, the mullion is deflecting too. I'm not gonna have the glass deflect.
Yeah, they're not totally moving independent of each other.
Right, exactly.
Okay.
Yeah, so I'm not measuring the glass deflection from what was the vertical piece of glass to this point. It's, the glass itself, the head of the glass has already come back in. And then I'm measuring from that theoretical straight line from the top to bottom, this kind of angle for the deflection. That doesn't come up too often, but that's how we look at that. So yeah, so L over 175, 3/4 max for dimensions 13'6" or less. And then if I'm over 13'6" up to infinity, it's L over 240 plus 1/4 would be for the deflection.
So if your calculation comes up that it over deflects, the result means we either have to add steel or we increase the size of the mullions. Is that right? Those are the two things.
Yeah.
So if the glass over deflects, what's the options there for the glass?
Thicker glass.
Just thicker.
Yeah.
Okay.
Yeah. Exactly.
So that just kind of helps you see when you see why we went with a deeper system or why we need steel. It's to counter the over deflection.
Right.
Okay.
Wait,
Question? Mhm.
if the glass over deflects, you get your glass, but if the what over deflects?
If the vertical member, the aluminum,
Okay.
the vertical
Okay.
over deflects itself, then we have to stiffen it. And so that's when we add steel inside of it, or we go with a deeper vertical member that's stronger.
Or kickers or
Or,
something.
yeah, we add an
We
extra
have to
anchor
somehow
point
limit the deflection.
so that it
Okay.
doesn't over
And so,
deflect.
yeah, you can either reinforce it, add extra anchors, or increase the strength, the properties of the member itself by going deeper or wider, deeper typically. And then for the glass deflection, really the only thing you can do is make it bigger. Yeah, to resist the bending. So so in the tributary, so when I'm looking at the vertical mullion, this is the tributary area that's going into that mullion. So it's the half of the bay on either side. So like in this one over here, the wind load on this vertical mullion is from there to there, because it's half of that light of glass, even though it's small, to over here. And then on a jam, it's just a small. The jams just get half of whatever that bay is that it's up against. So when we're looking at deflection of the vertical mullions, and so then, but now when we look at anchors, tributary area changes. So when I'm looking at the anchors of this vertical mullion, the dead load that's going into this, there's wind load and dead load on that anchor, right? So for the dead load of this anchor, the tributary area is the same as that. Because I've got a setting chair here picking up half of this light of glass, and a setting chair here picking up half that light of glass. And then half of that, there's a setting chair on either side of that, which is coming to the vert, coming down. So for dead load, that's my tributary area. For wind load on that mullion, let's go orange. For wind load on that anchor, that's my tributary area. So it's because the head anchor's taking this wind load. Because the wind load is applied to the face of the wall, right? So as we go to figure out what the anchor is here, it's half of that. It's half of the height. So anchor to anchor, half of it.
So tributary area really only is calculated to verify the anchors of that mullion. So again, it's not deflection anymore, or is it also calculating deflection?
We're just looking to define. Well, I was just trying to define tributary area
so I'm
in
just
the
saying,
different cases.
why we need to know what tributary area is.
And for
it
deflection,
affects,
and
it does affect deflection.
Well, because that's the first.
That's
one.
what you
That's
use.
the first one we looked at.
To measure, yeah.
Right. Yeah. So this blue, yeah, exactly. So
that's what you use to calculate the deflection of the vertical.
well, so that blue tributary area is used for deflection of the vertical, and it's used for dead load of this anchor.
Okay.
In a strip window. So we're looking at a strip window right now. Curtain walls will be a little bit different. And then for wind load anchor on the anchors, it gets divided like this. And then if we go to so that was one right there. If we go to a curtain wall, it's a little bit different. So our unitized curtain, so tributary area is still the same as far as, but now let's say, looking at this, I'm looking for the deflection of this vertical mullion. So again, my tributary area is going to be, so that's the tributary area for that mullion. And this jam gets, the rest of it over here. Actually, indoors, it's a little bit different. Let's maybe come back to that one. Sure, there's a curtain on this job somewhere. Maybe. There
you go.
So yeah, so the tributary area on that mullion for wind load is right there for deflection. And so then this anchor, hey, I have an anchor at the floor line here, and I have an anchor up here, and then there's a cantilever down here as well. And so there's a deflection criteria for cantilevers as well. It's typically 2L over 175, so twice the length divided by 175. And so that length here is the length that cantilevers past the anchor. So as I look right here, I've got 9.5 inches. Down here so 310 minus 9.5 is 3.1. So 3.1 from the top of the floor. So let's say the anchor was 3 inches down from that, I'm 210. So that's 34 inches. So it'd be 2 times 34, 68 divided by 175. So 68, it's almost a third. So I'm allowed about 3/8 of an inch, 5/16 of deflection. Let's call it for the cantilever portion itself. So just this end point down here, what it can be. But as I'm counting the deflection, it's not just anchor to anchor, it's actually the entire length of the mullion in this particular case. And then, similar to the stick wall, because we dead load at the top, this is my tributary area for dead load as well. And so even though this is 2 separate units, this anchor is taking the right half of this unit and the left half of that unit. And so that's the total amount of area that's the dead load on that anchor. And then now where it gets fun for us is going to be on the wind load. So on the wind load, on this anchor down here, it gets all the wind load of this lower half, the cantilever, but then this anchor gets half of the span up to the next anchor. So the wind load on that is going to be there for that lower anchor there. And then the wind load for this anchor is actually going to be, it's actually going to come up like this, because it's catching the other half of that lower unit, but it's also catching the wind load of the bottom half. And so it's really catching 4 corners. It's catching 1, 2, 3, 4. So it's really catching a fourth of the load from 4 different, but it really just comes back to really just being 1. So typically well, this is the way it gets, the way we really determine our tributary area is typically by the bay width, 5 feet, by the height, 14 foot.
So that's the wind load of the tributary area?
That orange there is the tributary that's getting applied for wind load to that dead load anchor.
Okay.
So it's actually, and so what's sort of funny, ultimate stuff, I'll call it funny.
Engineer humor.
It's engineering humor, and I'm not even an engineer, but I'll laugh. Is this tributary area and this one, is, if it wasn't for the cantilever, if it was normal, is typically the same area. It's just you get to them in different places. So really, as we're looking at it pre-engineering wise, typically I'm getting a 5 foot by 14 foot, so I'm 70 square feet times the wind load. And then I'm just applying that as dead load and wind load. So that even though it's offset, and then when you get to the bottoms and cantilevers and tops and parapet caps, you might have some larger tributary areas and things like that. But for the typical walls, it's really just the typical bay by the typical floor to floor, and it gives you what you need. So. Is that making sense, Amber? Okay, perfect. Just check in, make sure. I don't want you to feel left out. And so then and you'd have something similar, of course. At jams, right? So at a jam, of course, it's going to do that. My wind load on that anchor is it's again back to quarters of units as far as the wind load. So so that's picking up a quarter of the wind load there and a quarter there, and applying it here. And then as far as dead load, it's it's half of the unit below. And so then sometimes we run into cases where this upper unit maybe doesn't go up to a floor, but goes up to a soffit. And so in that case, those units are actually dead loaded onto the unit below. So I might end up having, this tributary area for dead load applied to that anchor also. Doesn't change the wind load that's going to that, because my wind load was already skewed up. But when we look at the dead load, and then the other half, the wind load would be up here, just like it is on this one already. So the only time that really happens, is when we come up to a soffit or something like that. I don't actually get to a floor where I can have a Mac anchor and put the dead load clip up there.
Just while you're on that, maybe could you go over those symbols that are right there on that elevation?
Sure.
Yeah, because that'll kind of tie into that.
Yeah.
How
So,
it's indicated on the drawing.
yeah, and so then, the symbols we use for our dead load and wind load, we have a triangle that used to be filled in. Looks like it's hollow now. Maybe it's a rivet.
I think that's just a rivet thing.
And then, so we use triangles for dead loads and circles for wind loads.
And so that's why you could see at level 3, you have both symbols because it's taking both dead load and wind load. But it also shows, for the way I understand, helps me understand too, is the X's of the units. Each unit needs a dead load and a wind load. Is that true?
Yeah, what's weird is I never thought we put the wind load typically, unless it was a specific anchor. I mean, I never knew we did that.
I think we do that on every floor.
Is that what we're doing now? Yeah. Okay, interesting.
But I think it's just also partly because with the units, I said, I think it's a good back check to see that each unit X has both.
Okay.
So that's kind of, so again, we
So
put
that's
it on the
the
left
standard?
side,
Okay.
yeah, and it just assumes it's applied to all the units going across, unless there's some anomaly down the line. Then I've seen like Mike puts the symbols actually in the middle of the elevation if it changes.
Yeah.
So, but section wise too, we show those same symbols. So you
Yeah.
can see here the strip window, the dead load's at the bottom,
Right.
and the wind load's at the top. And then that mini Mac that we call it, that you see in your head details that comes down, that's a wind load connection. Yeah, that. It's not a hard dead load.
Right. And so I don't know. And so then coming back to our doors, so this will be a little bit of what Ezzy was saying. So, well, this was all doors. So, but normally where this would have been dead load over wind load, at our doors, we do dead load at the ground. So I don't know if we cut another larger elevation maybe. Curtain wall with the door in it.
With that one on, yeah. That one.
So it's weird because I would guess that So this one is dead loaded at the sill. And then wind load, that's, yeah, because of the door, but I was trying to look for the shift like you were talking about, Esley, but I don't see one on this. So this building may not have had one.
Or maybe there, where the step was. Or even that other one, where that step. You see that maybe,
Yeah,
Oh, no, but see-
so
see how
here,
the
so here
symbols,
you
yeah.
can see they've added some symbols here where it changed. But again, that dead load's up there the whole way anyhow. But because it was different, they added them
they
in
just
there
wanted to make
separately.
it clear, yeah.
Yeah.
Maybe that other step one might. Maybe not.
But normally, if this had been a big full elevation and then all of a sudden it had some doors over here by the dimensions, it would have had, you know, a wind load connection, dead load, wind load down here, and then over here, we would have put in dead load, wind load to indicate specifically. And the only difference is they just take the jack screw or adjusting screw out of the hook lug. It's really taking the dead load, and so now they shim hard underneath.
Could you just show it real quick, what you're talking about last time? I don't know, that's a kind of new term. I haven't shared that guy with you guys yet, the jack screw.
So the thing that's missing right here, it's missing in this detail. Let's see if we can find a detail that's actually got it. I think there's some curtainwall on this show
Yeah.
somewhere. Oh,
There you
went the
go.
wrong direction. So it's this screw right here.
So by having it, that's your indicator, that's a dead load anchor.
Yeah.
When it's removed, like that first detail, that's the wind load. So that's your visual cue in the details.
And so
Because
it-
that's,
yeah.
yeah, putting the pressure and the weight on that anchor bolt, that's a big 9-inch, 11-inch long
Yeah.
bolt.
So if you take a tour of the shop and you see the hook lugs on the units, you'll see this bolt is pre-installed. And so there's actually a nut right here with a nylock washer on it. And so that nut's held in place. And so then the bolt, they can screw up and down to get their final adjustment to get the unit set to place. So with this, the little sawtooth serrations here, the field can get this mat clip within, they tell us, 1/8 of an inch is what they're targeting, plus or minus 1/8 of an inch. And then this, then with this thing, they get where it's bearing on the 3/4 inch bolt coming across, they get their final adjustment up and down. Let's see if we can take you to it.
This is the plan.
So again, yeah, this is the bolt right here that's doing the adjusting up and down. And so all the dead load is going through it. So it's going through that into the 1-inch clip, back over into the 3 screws that are holding that hook lug onto this. And it's all bearing on this bolt. And so then as our engineers look at that bolt's under dead load deflection, right? Because it's getting the load. It's supported in 2 spots, you know, here and here. So that's where it's going to be. And then the load's here. So it's going to be trying to bend in wind load. And then it's also bending, or dead load. And then it's also bending in wind load. It's bending out and from the same points. So there's deflection on bolts too, not just the mullions and glass. Okay, so that was tributary. Oh, well, I was going to say that it's just a little small thing, but on the doors, our tributary area just gets a little larger. Oops. So on doors, just because of the flag units, and actually this one looks like it's got a full vertical, so it may not. So that vertical is coming down. It's taking the, you know, the wind load tributary area, but a lot of times our doors, you know, the door unit might look more like this or something. And so now the tributary area changes just a little bit on how we have to get it. It's maybe wider than 5 feet. Maybe it's 5 feet plus half of this other little one or something like that, depending on how the doors are made. But generally, it's, you know, what we've discussed, and then there's always going to be some special little circumstances here and there that apply.
So is that, so just to clarify, so then for doors, is it logical then, because just depending on the unit breakup, is that why usually around doors you need a little more stiffening or a little
Yeah.
more, but it's not necessarily because of the force of a door, it's just because the way the unit is broken up,
Yeah.
it causes more
Right.
tributary area.
Right.
So it's not necessarily force on the door.
Yeah.
Because initially I was first thought like, oh, it's because there's some kind of door loads we have to account for, but it's not.
No.
Okay.
Not too much. And so like, and let's say this was a flag unit, for whatever reason. You know what, I'll just draw it to there, because that's normally what our flag units look like, is something like that. And then if I'll draw another one over here. Whoa, it got really big, didn't it? Oh, it's because that's two pairs. But if I've got that, you know, in this one, the mullion actually came down, but let's say this mullion doesn't come down.
Mhm.
So now I've got an anchors over here for dead load, anchors up here for wind load, but I really don't have anything holding this corner for wind load. And so invariably what we have to do from the engineers, we have to put some sort of member across here to really tie those two together so that they can't just bend in, because you're just gonna wanna, because there's an anchor up at the top and there's an anchor down here. And so it's not really a function of the door, but it's a function of the wind load on it. So we either put a 1/4 by some that 4-inch steel plate across and then we're bolting them together, or it might be something in the header. But we've got a corner of the unit that doesn't have any support. And it's just gonna wanna bend. I mean, we could put a kicker also, you know, if we wanted to put an anchor here and kick it back up diagonally to the floor or something. So there's different things you can do. We can have like a little, you know, Mac anchor right down there, taking that wind load back somehow. And a lot of times, usually it's not ever 5 feet like that. It's, you know.
Well, we could just imagine those were single door
Yeah,
leads or
exactly.
something. It was
Yeah,
half the size,
exactly.
but it's a good visual to see what
Yeah.
you're talking about. Yeah.
Right, but we end up with two corners of a flag up there, just sort of flapping in the wind, like a flag. So tributary area, wind load, dead load. Okay.
Just wind load, dead load, before you move on, could you maybe just show how we show wind load, dead load at the sills and at the heads? Just again, like the mini Mac, but
So you mean this?
yeah, because we went over at the
Right.
anchor, but maybe not, we didn't show like the notching at the sill.
Oh, you mean on a detail?
Yeah, if we could, just to show how you would indicate it or how you would see it. What's the difference and how do we show it?
Well, so on the strip window, it's always dead load at the sill.
Yeah.
And so they've got the note here, says notch vertical, sit hard on the sill member. So really, the dead load of the unit is coming into the top of the chicken head through a notch in the vertical. So even the glass that's sitting in this sill member, it's the weight's into the sill, but then it goes over to the verticals into these screws. Now the weight's transferred to the verticals. And then it's this notch in the vertical, which is actually transferring the load.
Do you see, that line work there?
So
Yeah,
somehow,
trace it.
somehow.
Yeah, so that line work again represents the notch in the vertical member. And so it's sitting hard
We said
on
hard
that
right
chicken
here.
head, which is what's making it a dead load, because it's not moving, it's hard. And then we usually have that note there, notch to sit hard, and that represents a dead load at a sill.
Mhm.
Okay,
And then above that in the strip window, you just got the mini Mac here, which is just a little, it's just a lug, and the units are just
they
sliding
just
up
slide,
and down.
yeah, there's no fastener, they're not pinned in place, they're allowed to
Right.
move, because that's a wind load.
The best way to see that is go out to the field. I think our shop right now, I think Bob just mentioned we're setting these right now into the precast frame, so the shop is
Yeah, we saw
window
those.
boxing these.
Yeah.
So you probably saw the mini mat clips, and then you probably saw this out there. When you were looking at that, that's what you were seeing, so.
You should go out there.
Which one?
Ask Gabe to take you out to the shop B,
Oh, yeah,
and
shop
then
B.
you'll see them actually installing these units, and you'll see those clips and the notches, and then you'll see the notches and verticals, because all the units are laying down on a pallet, you'd actually
Oh.
see it. So
Okay.
I'm asking you to take your little field trip.
And then it was weird that we used a strip window sill on the bottom of this curtain wall, so I can't show you the details. I would have expected that to be
Yeah,
a strip.
that's what-
That one would have been a strip window, but the curtain wall I would have thought would have been
There you go. You've got that one.
a curtain wall. I'm looking for the sill. This may have been all. Play with that. Where's that elevation thing notch? Oh, maybe this is-
We can use the stack maybe as an example, maybe.
Yeah, I was just trying to find one that had the notch. for it,
Yeah,
but-
yeah, it's a little weird, but there's not.
Yeah, it's all soffits. And so at the stack joint or notch, is, you know, because this is an expansion, right? So the dead load and wind load symbols that you were seeing on the elevations, you know, this unit is dead loaded down here. The bottom of the other unit is transferring wind load through the chicken head. So this chicken head is actually what's taking the wind load of the bottom half of that unit. There's not actually a separate distinct anchor. And so that's the notch, you know, that's allowing for, you know, this volume, this unit can go up and down as the live load of the floor above goes up and down, or as the floor below moves down, you know, in essence, it's gonna do this. And so within our system, I don't know if we mentioned this the other day, but, you know, we've got 3 areas that we're allowing for a movement. I'm gonna allow for movement here. I'm gonna allow for movement here. Then I'm gonna allow for movement here of this chicken head when it's moving without the unit above. So the floor above that this unit's attached to, as it's coming down, you know, all this is coming down. And it's, you know, for 3/8 live load, and then we have, you know, a little more room for thermal expansion, and then maybe a little extra 1/8 of an inch or so for just, you know, tolerance of building our units and things like that. And then as the floor, let's say this floor doesn't move and the floor below moves, the chicken head is gonna lower. And again, I'm gonna raise this one up just to show it, but we've got that same 3/4 of an inch right here so that we don't lose the engagement of our air seal, water seal gaskets. It has to stay in contact with the back of that horizontal. Is that floor below that it's attached to moves, but the one above doesn't.
Right, so then we'll see that when we start looking at more details and we see more jobs, the height of that chicken head will vary because of that, right? So we call our standard, but then if the building is moving more on another job, that's when you'll see taller chicken heads, or you'll see taller sill members to account for that movement. So it's not always what the architect may want, but it's what they need to accommodate the movement of the building, right? But that's how we account for it, because we need to, like you said, keep it engaged.
Yeah.
For all the
And so-
moving scenarios.
Yeah, so if it's a 1/2 inch live load, it's only an 1/8 more. But the thing is, I need that 1/8 of an inch. I need an 1/8 of an inch here.
Or otherwise
I
it'll
need an 1/8
bottom
of an
out,
inch
it'll
here.
hit. Yeah.
And I need an 1/8 of an inch here. So it's really that 1/8, I really need 3/8 of an inch to accommodate it. And then if it goes to 5/8, I add another 1/8, 3 times. So my Southern California office, brothers, sisters down there, they've sort of cheated this number. And I keep telling them and they don't care. They just keep cheating me. So they'll increase this one and this one, but they're a little lax about this one here. I just confirmed it with them in our system design meeting that we're taking care of that in all 3 spots. Because I need to, it's all
So
three,
what
all
does that
three.
mean? They make their die,
They leave-
still die, not,
They make this one 7/8 and this one 7/8, and they leave this one 3/4.
so that's me, so they make their die of the sill not in line with the notch. Because right now the back notch needs to match with that
Well,
to keep the same dimensions, right? Because if that notch bottoms out, the bottom of that sill is.
what's gonna happen the way they've got it is it does that. Where I want that to stay right there, when the bottom, when this chicken head pulls down,
Yeah,
I don't want that gasket, so, but they're like, yeah, it's fine
oh,
like
let it
that.
go up a little
They're
higher.
fine like that. I'm like, yeah, well, not really. Well, I mean, maybe, but it's not how I can only suggest. And so then when this is in a dead load condition, so maybe it's at a sill can next to a door, or maybe it's got a soffit above. What they do is they just modify that notch so that it sits hard right there on the chicken head. So now the dead load, again, just like the other one's transferred into that chicken.
Is that cool? Good?
Mhm.
Okay.
So then we have, what do we got there? So next up was going to be, looks like it's the racking versus translating. And so I think, did we talk about that a little last week or no? Maybe not.
Does it sound familiar, those words?
Racking.
They would only come up once.
Racking.
Twice. Racking, translating.
You'd probably remember.
No?
it.
Okay, yeah.
So,
You remember a little bit? Okay.
so I moved things on the board. So Michael, hey guys, let me get behind you. So I'm gonna sketch over here so Amber can
We
see
can
as opposed to the sideboard.
do a preset, I think.
Well, I appreciate that.
Because it was on the side last week and you got to see just a little bit of the glass, but I figured this week that would.
Yeah.
Oh, there we go.
You're truly the teacher.
Yeah, oh my God, it's scary. What they need is, you've seen those glass chalkboards when they write behind it, but
Yes.
write backwards. I don't know how those guys do it. So racking and translating, so when the building moves, the floors just are moving, in seismic. The columns are, a vertical column, say floors in between, in seismic, the floors are just sort of moving each floor, and then this floor comes over, and then it just goes back and forth, doing its thing. So now it's up to our window system and any other product that's on the building to move with the building. And so there's 2 ways that you can move with the building, is it's doing that. So I've got and we sort of look at them as 2 different ways. Our unitized, we typically design that it's gonna, and we say that it's gonna rack. Actually, it's gonna rack. Well, actually, all of our systems rack, but the way they rack, the way it looks is a little bit different. So our unitized, when it racks, and actually, I'll just say something about translating first. So in translating, the whole thing, everything just moves. It doesn't change shape. It's a square. So this happens like with precast or GFRC, typically the heavier, more monolithic elements on a building. Windows are pretty flexible. Aluminum, they're a little joinery and things like that, they bend a lot. But precast, GFRC, they tend to just be heavy masses of stuff, and there's not a lot of flex in them, so they just move horizontally left to right in seismic. So if they're dead loaded on the building here, and then as the thing moves, right, that load, those things just move. And now their thing maybe is hanging off the edge of the building. And then when it moves the other way, it's inside the building. So now it's doing this, and the building had sort of done that thing, right? So it's actually moving over. So when translating elements, usually have fairly distinct horizontal slip areas or slip joints at every floor. So usually it's a floor by maybe a bay wide or something that's moving as a big mass. And so you've got this thing that's just moving. And so there's still joints between each other. So I've got this element and it's just moving back and forth like this. But our unit types, so that's what translating is. It's really just, whether it's, tall, and it could be any shape, really. It could be like this, but if it's just moving left to right horizontally, that's translating. And so for us, for racking for our units, and so as a unit, I'm a square, we consider that it's going to stay rectangular. It's going to keep its primary shape, and it's going to do like this as it moves. So as this floor, as this floor moves this way, now my units, they've maintained their shape, but because of their anchorages, and this is the floor line. So this one is lifted off. This hook lug is lifted off its bolt, but it's still engaged with the vertical adjacent to it, so it can't come out. And now the dead load is really just on this one hook lug on this bolt. And then the same thing here. This unit has come off of that one, but its dead load is still there and it's still engaged down at the sill. I'm grossly exaggerated. It might lift that much, but if you consider that this point is usually 5 feet away, but it would never tip to that degree. So our verticals in the male-female connection, everything slides. There's not much difference in how that looks as far as the width of the mullion. The 2 3/4 might separate a little, it might get a little closer as it's moving, but in general, it's staying relatively 2 3/4 as it's moving that way.
But you're kind of assuming the units next to each other are kind of moving the same. Is that correct?
Well, because they're all attached to the same floor.
Right. Yeah. So that's
Yeah.
kind of assuming they're shifting
Yeah.
together.
Yeah,
Yeah.
everything's leaning together. Does that sound okay to everyone?
Yeah,
Sound good? Okay, we're done.
pretty straightforward, yeah.
Huh? Pretty straightforward, okay. Yeah, and again, we're just talking the general terms, getting you familiar with. And so on our stick walls, so if I was doing that on a stick system, I've got. And so, do you understand what I say when I mean stick wall? So it's field installed. It's a bunch of parts and pieces. Go out there, erector sets, put it up, and then put the glass in. Right. So I've gone out and I put my verticals up. And then we put our horizontals in, and then we put our glass in. So I've got extra horizontals there. So so everything in the unit sort of gets squared there. So now when this one racks, and it's still racking even though it's a stick wall. So now this is moved this way. But my horizontals have stayed level. Wherever it's at. So in the stick wall, the mullion's racked, the horizontals stay horizontal. Because if this one's going over 3 inches, this one's going over 3 inches. So it's probably come down a 32nd or a 16th, but the actual dimension between the verticals has stayed the same. And so then this is an issue for us for glass, because the glass stays square. So now I've got rectangular glass and a parallelogram opening. And so in stick walls, there's different engineering we do for the glass and making sure there's clearances and glass isn't going to hit that we don't necessarily do on unitized. Because on unitized, the opening has stayed the same as the glass. And so there shouldn't be any issues with that on unitized. And yeah, so for us, windows always rack. Other things can rack and or translate depending on how they do it. So then where we run into issues is when I've got this translating element right here,
Right next to
right next
racking.
to something that's racking. So as I'm I'm on this side and it racks, because I'm attached, that translating element's attached typically at the floor too. It moves over, I've just got a big joint right here. But now let's say that translating element's over here on this side, and my anchor is right here and it's right here. So now as this pulls over, we've just run into each other on the one. And then when it goes back the other way, I'll have plenty of room over there and I'll hit on this side. So when we run into those situations, we have to design those substrate sort of details to not have that issue. So either we can have larger joints, or we can, if products are maybe recessed in, maybe products stop short of ours so that we eliminate that overlap. So either we move behind, typically it's precast, and we design our details so we can move behind it so that it still translates, but because it's out front, and then I've got a joint in a different location, then we don't actually hit no material hitting. You have caulk joints being exercised.
Can you roughly sketch that detail though? Just what you just said, like the vertical and then how we put the precast in front?
Yeah.
Do you want to show one or
Oh,
this might be
do
easier
you
for
want
you
to
to
switch
sketch?
back for?
Yeah, I'm just saying because I don't know if you'll find one. I'm just saying so we could visualize what you're saying.
So this is my precast, let's say, and then here's my window mullion. And so then how we do it is we put an angle here. It's attached to the mullion. And so now this element here, so our window mullion here can rack, and this precast element can translate.
But it's in front
And it will
of
be in front of.
our windows so that it won't hit.
So normally that detail for us would look like that, and our window would overlap it. We would have a caulk joint over here.
So that's when we're moving together.
So yeah, those would be when we're moving together. And then, so this is racking with us, but then if it's translating, so in this case, this element is doing this as well. As long as whatever it is, whether it's plaster or precast or whatever. So as long as we're moving together, we're okay. And then when you have seismic moving the other direction, this panel that's translating this way, it's just leaning out, same as our windows are leaning out. So there's no issue coming this direction. It's in this plane here.
And so then that caulk joint size becomes what we just engineer to stretch and not tear with the amount of movement.
Yeah, so then this joint has to stay watertight and elastic, which is, usually around 3/4 of an inch. And so a 3/4 inch, and so it's really designing for, for that to come over 3/4, and then the seal will be this
Seal it
long,
stretch, but it has to stay. Like you said, it can't tear.
So so that joint might become 1 or 1 1/4, but because the architect can't see it from the face this direction, he's seeing a nice little small 1/2 inch joint. But when we apply that angle to the mullion, he's less concerned with that joint getting larger to take that movement from the side. So it'll be referred to as a slide-by condition. So you may hear it referred to that. That's what precast calls it.
Oh, yeah?
And so we said, fine, if that's what you want.
So there's some more terms there, you say?
Slide-by, yes. So slide-by is how precast refers to that. So. And so there are occasions where, and probably what you guys saw, I'm sitting there looking for it, it's staring me in the face. It's right there. So we have to take it off the board. I have to leave that on there. In a window box condition, so a window box, you said they were out in the shop.
They saw the shop,
yeah. Saw that? So
yeah, so
window
like
box.
punched
Again,
openings, right?
so our precast company.
There's another word, window box.
Window box. If they build a 15-foot by 30-foot panel, it's got 3 openings in it. So that's one thing. So that panel is translated. That whole thing is translated, and my window is inside of that. My window is really gonna just translate.
It's like stuck to.
Because once it's in there and it's caulked all the way around, it can't go anywhere. It doesn't matter if I designed it to rack, it's not going to, because the caulking is going to keep it in place. So in a window box condition, that's really translating as well. Even though the window is designed to rack, it's just not going to. There's just no way it can rack because
what it's attached
it's completely surrounded.
to.
So in a window box, this, even though the GFRC or whatever this product is translating, I'm translating with it.
So
So
we're
this,
fully within it.
yeah,
fully
so that's what you were seeing
Yeah.
out at Moffett Gate, on the Moffett Gateway pen. But then where, that stops, and then all of a sudden you got a curtain wall going up. You'd have to
That's
look
where
at
you
that.
would accommodate. Okay.
So we're at 10 o'clock, Esme,
Yes.
so I know I didn't get through your last two, but I can always,
What
or
was the
maybe we
last
did.
two? I
Oh,
forget.
it might have been, one of them was showing the anchors, and so we actually
I
talked
think we
about
did,
that.
yeah.
Thermal expansion is splice, it's, so we can.
Okay, well, maybe we can set up another one
Yeah,
after that.
yeah.
Okay, cool. All right, thank you.
All right,
Back to the room.
thanks, Amber.
December.
Thank you.
Thanks, hello.
You bet.